Hello, welcome to lecture 2. This lecture is about viscosity, surface tension, and pressure. Uh, the objective is to learn about viscosity, how to estimate the force, then learn about surface tension, and one of the application of surface tension is obviously capillary, and capillary effect is another side that we will look into, and determine the variation of pressure in a fluid at rest, which we'll discuss how to measure the pressure, how it is varies, and then we go further. Okay, what is viscosity? Is a measure of how a fluid resists to deformation or internal resistance of a fluid to motion. Let's say, for example, consider honey and then water. You see, when you want to pour honey, how slow is moving, and then when you have water, if you want to pour it in the container, how fast it is moving. This is basically because they are two different fluids, they have different viscosity. And this is the friction which is created between internally developed between different layer of fluid once they start to move relative to each other. Now this figure obviously shows different fluid that if we consider, for example, this is water, honey, oil, or get harder and harder. That harder means is more viscose basically. When they get more viscose, the movement is very slow. Okay, now in the context of fluid mechanics, if we want to understand the mathematics behind how we work out with viscosity, how we work out the force, this slide gives you obviously what we need to learn and capture. Now consider a plate, the fluid between two plates that we discussed as part of the lecture 1, and then the top plate is moving with we apply force F, and then when we apply force F, obviously it moves with the velocity of V. Then what we said before, we said the molecules of or the fluid adjacent to the plate that has zero velocity, which is the bottom plate, the velocity here would be 0, and then the velocity of particle at adjacent to this surface is the maximum or maximum velocity that this upper plate is moved. How the velocity is developing, you can see the velocity in this case developing linearly, increases, and then obviously if we want to estimate the force, suppose that we want to move this one with 1 meter per second, then we want to know what force we need to apply if we want. Obviously there are a number of things which is important in here. How far these two plates are, how fast we move it, what's the surface area, these are, and what's the fluid between the two plates. Now if we consider how, because this is a shear force, we're saying force is equal to shear stress times surface area. This is how we estimate the force. Then obviously we know that this force is directly depend on the surface area. What that means that if the surface area is larger, then the force we apply is higher. If force also directly proportional to velocity, means that the higher the velocity, the larger the force would be. However, the force is inversely proportional to the distance between the two fluids. That means the smaller the distance, the larger the force we need to apply. So these are the factors that influence basically this force, considering this figure. Now, okay, now moving from here, then now we can write a relation between force, surface area, velocity, and the distance between the two plates based on what we discussed here. Then we go further. If we want to have a equation, then this force, we can say force is equal to a property of fluid, which is viscosity, mu, and the rest is surface area, velocity, and then obviously the distance. Now, if the velocity, one thing we need to consider, if the velocity change linearly, that's okay, we can write velocity over L. However, if the velocity does not change linearly, for example, then we need to write the equation in terms of derivative and say change in velocity change with distance, how velocity changes at different distance from the plate. So now we can put it in this way. Force is equal to shear stress times surface area, which is equal to this portion which we developed here. And then, okay, this is du dy. If the velocity change linearly, we put v over L, because there is no difference between u and du if it is changing linearly. However, if it's changed non-linearly, then we write it in this form. And then shear stress, basically from this equation, now you can see that the shear stress is mu times velocity divided by the distance. Okay, what mu is called, it says, is a property of fluid, which is called coefficient of viscosity. And in the form of mu, we call it dynamic or absolute viscosity. Important to memorize this one. It is called dynamic or absolute viscosity, and its unit is kilogram meter per second, kilogram meter second, or Newton second per square meter. Or we know that Newton per square meter is basically pressure, which is Pascal, and second. That means three different units you may see here, which have same meaning. One thing you need to realize that we have another item is called kinematic viscosity. What's the difference between kinematic and dynamic viscosity? Is the difference is that this one, when we divide dynamic viscosity with the to density of the fluid, then it is called kinematic viscosity, which is meter square per second, or a stock, or one stock is 1 centimeter square per second. This is what is that. I hope that you go through this material again, because this is important and helping you to answer many questions. Okay, now how the basically, if we go back to previous slide, and then we see that how basically we want to see how the change now in shear stress versus rate of deformation happen. In here, shear stress with the rate of deformation. This is the rate of deformation, and this is the shear stress. That means if we plot this one versus that one, we can see that shear stress with the rate of deformation for oil changing linearly, for water changing linearly, for air also changing linearly. So what conclusion we want to make in here? Those fluid that they share a shear stress rate change linearly with the rate of deformation, they are called Newtonian fluid, which in this category we can say oil, water, and air. However, we have fluid that the shear stress does not change linearly with the rate of deformation. And these are, for example, Bingham plastic. You can see, yes, here is linearly, but it's still not linear, because you need to apply some shear stress first before the material deform. This is called Bingham plastic, and some of the plastic happen in this way. We have also cases that rate of basically shear stress versus rate of deformation change non-linearly. That means if we have a power for this equation, that means this power, we call it n, and this n, it could be basically, if I put the power here, I put it here, pen. If I put right in this way, n, this n can be positive, can be negative, or can be equal to 1. If it is 1, it is Newtonian fluid from what we see in the next slide. Now, if it is greater than 1, it is called pseudoplastics. If it is 1, it is called Newtonian. And if it is less than 1, it is called dilatant fluid type. But then remember, we have Newtonian fluid and non-Newtonian fluid. Non-Newtonian fluids are those that rate of shear stress does not change linearly with the rate of deformation. Next is, okay, what's the difference between viscosity change with temperature? Because, okay, imagine if you heat up honey, it moves faster, but if you cool it down, it moves slower. So for liquid, we say as temperature increases, basically viscosity reduces. That means less viscous fluid. And you can see one of the things that you need to consider, viscosity change with temperature. However, for liquid, as we heat up the liquid, the viscosity reduces. However, for gases, this increases. Why this is happening? Because in liquid, the molecules passes more energy at higher temperature, and they can oppose the large cohesive intermolecular forces. That means when we apply heat, intermolecular forces reduces. However, for gas, the intermolecular, when we apply temperature, is basically negligible. But the higher temperature, it causes that gas molecule move faster. That means if we heat up the gas, you can see the molecular activity increases. Then by increasing the molecular activity, basically viscosity, more collision take place between molecules, and then in this case by increasing temperature in gases, viscosity increases. That's the difference between the two. This table, if you consider, for example, the table on the right shows dynamic viscosity, or mu, which we say at 1 atmospheric pressure and 20 degrees Celsius for different material that we can look at it here, water, mercury, oil, and so on. Then you can see in here that SAE 10W, SAE 10W30, and this is if you want to buy, for example, oil for your engine in winter and in summer, you have to put different type of oil. Why? Because in winter is colder, then more viscosity. However, in summer the viscosity would be less, and then that's why different various type of engine oil they putting in there. However, in Australia, because the variation of temperature between winter and summer is not significant, then you may, they don't do that. But in cold area or cold region, it's happening. Now, Okay, but table figure on the left hand side, obviously it's showing for different material change of absolute or again dynamic viscosity, because we say dynamic and absolute viscosity are the same, showing for different material with temperature. You can see for oil, for air, for hydrogen, many of them you can find it in here. That's good because you can then work out for different material. How about if there are material here that you don't have access to this information, you can look at the textbooks or relevant textbooks or internet search, and hopefully you will be able to find it. Now the question is that, okay, for the fluid that we don't know, and it is happening in many industries, sometimes they developing new material, then they want to measure the viscosity. One of the equipment that they normally use for measuring viscosity is called rheometer. But if we want to see, we are not, because there are different type of rheometer, we are not discussing that, but we just want to discuss the principle of measurement. Now, imagine you have a shaft in here, a larger cylinder in here, which you normally fill between these two, the liquid that you don't know what its viscosity is, which is basically yellow, this area here, and then which is this area basically here, and then you want to see what's the viscosity of this one is. Now, this outer cylinder is a stationary cylinder. Sometimes it can be reversed, but anyhow, in this case, it is stationary, but this shaft is rotating. Now, imagine. Okay, we said the fluid adjacent to that one, it has zero velocity. However, the one adjacent these two rotating shaft has got maximum velocity, and this is how this figure shows how the velocity change linearly in the shorter distance. So, if we want to estimate the torque for this shaft which is rotating, we can see that the torque would be F times R. That means the force times R. Then this force basically is viscosity based on the distribution of the velocity here is viscosity. Now, what will happen? Okay, we put it in this equation. What would be R? R would be the radius. What would be the surface area? The surface area would be the perimeter of this shaft, which is 2 pi r, and normal to the page is length of this shaft, depend on what length would be. For example, if it is this length, this is L, and then this is what it is, and then you put it in this equation, then you end up with that one. Then you obviously, the number of rotation, you change this angular velocity to number of rotation, and then at the end, you end up with an equation which enable you to estimate the torque. Okay, now that you have torque, then imagine in here, now you measure the torque in here, then you have all other physical parameter, number of rotation, and then what is unknown here is viscosity. That means all other parameter, pi, r, n, l, and distance is known, but the only unknown here would be mu, then which is dynamic viscosity or absolute viscosity. Then you can also measure the torque, and then because you're rotating and you have a facility to measure the torque, and then from there the only unknown would be viscosity, which you can work out viscosity. And this is the principle of how viscosity meter, or how basically viscosity is measure, and they call it viscometer or rheometer or something like that. Okay, this is an example of using this equation. The viscosity of a fluid is to be measured by a viscometer constructed of two 40 centimeter long concentric cylinder. The outer diameter of the inner cylinder is 12 centimeter, and the gap between the two cylinder is, which is L, lowercase l, which is 15 millimeter. And then, sorry, 1.5 millimeter. The inner cylinder is rotated at 300 RPM, and the torque is measured to be this much. Then determine the viscosity. So you know the equation, rearrange it for the unknown value, which is in this case is mu, and then you can simply work out what the viscosity would be for this case, exactly similar to what we explained. Okay, another property of the fluid is surface tension. Okay, I give you an example of surface tension. Sometimes you can hold a needle on the, if you put in a container and water in there, you can keep the needle on the surface of the water without it going down. Or sometimes you can see an insect is sitting on surface of liquid without anything happen. Or sometimes you see a droplet is forming, and then, okay, I start with the droplet. Why a droplet is a sphere? Okay, what is holding a sphere? You can see in the surface of a droplet is like an elastic layer. That means molecules are attached, are on the surface. They exerting force, molecular force together, and forming a layer on the surface of the liquid. Because these molecules, they want to have, they attracting to each other. Then the droplet want to have a minimum surface due to these forces, due to these internal forces, and then droplet is like a sphere. Or sometimes you see a bubble. A bubble, for example, kids, they play these like with a bubble maker. They produce hundreds of bubble, and then if you attach this bubble, they burst. Now, how this bubble? This bubble, basically, why this bubble form? At the surface of the bubble, molecules are have a force attraction, and they want to have minimum surface. Then this is obviously what is the surface tension that you can see it. Now, looking at that one, the surface of the liquid act like stretch elastics, for example, similar to the droplet, or like a elastics membrane under tension. The pulling force that caused this tension act parallel to the surface and is due to attractive forces between the molecules of the liquid. The magnitude of this force per unit length is called surface tension. So in that case, if you have basically a sphere in this case, then what will happen? Let's say, for example, around a sphere, this surface tension act on the perimeter along a line. It's not acting on the surface. It's acting force per, basically magnitude of surface tension is force per unit length, which is called surface tension or coefficient of surface tension. And normally its unit is Newton per meter, which is in SI unit. Now, some liquid they called hydrophobic. That means the surface tension is such a high, when they pour on the surface, they don't make the surface wet. These are called hydrophobic surface, or they call it non-wetting surface. However, if you pour water on the surface, you will see it is spreading quickly, make the surface wet. Then in that case, they are called hydrophilic surface, which is this one. Now, in terms of contact angle, these are the comparison that you can make. Let's say this is comparison for this is comparison for that one. In terms of contact angle is low. You see contact angle is this one, which is in this case is low. However, for non-wetting liquid, then it is high. Adhesiveness is basically poor, good, and then wettability is poor, good, and then solid surface free energy low, high. These are the difference if you're comparing between hydrophobic or hydrophilic surfaces. How to measure surface tension? Obviously, if we have, for example, a U-shaped rod, which is in this form, and sometimes you see kids, they generating bubble, then imagine, for example, this U shape, and you have a rod which is going sliding inside this U shape. You putting the liquid between these two, then applying force in this direction, and once you move it, obviously due to a stretch, it will extend up to certain distance or certain forces that a membrane or a layer of fluid is forming in here, like this elastic stretching layer or skin basically. Then once it is start to burst, this is where is basically the surface tension, the force you apply. Okay, how you apply this force? Remember, if you're looking at the cross section of this rod, yeah, the cross section of this rod is circle. Now this surface tension act in this side and on the back side of it as well. That means when you apply force in here, which is the force F, then one surface is this one, another surface on the other side. That means the surface tension force acting along this line, but on both sides. That means one in here, and the distance which is applied basically. Now, okay, how then if we show the surface tension with the sigma, then it would be force which we apply in here divided by 2b. Why? Because basically this b, I should have said the cross section, because the surface tension should be this one. This is the b. My apologies. This part is section of this one. If you look at that one, this is the surface tension, and then this is the sigma which is applied. One sigma here, and acting what length? Two length. One this side, one on the back side. And then force divided by 2b, it is the surface tension. So it is basically force times distance. And this is how basically the surface tension acting on how surface tension can be measured in this case, depending on the distance is acting. So if we want to have a definition for surface tension, is the work done per unit increase in the surface area of the liquid. Basically, this is how we can measure the surface tension. Okay, now if we want to extend the way that we estimating surface tension for bubble and for a droplet, we want to see what's the difference between bubble and droplet. Okay, why? Okay, imagine you have a droplet in here, like here, and you cut it to half. Surface tension acting along this perimeter as we explained. Now, then the surface tension acting in this way to hold, surface tension acting in this way to basically hold this droplet like a sphere. Now, opposite to this, okay, this force need to be balanced by another force. What is another force? When this surface tension apply, then create a pressure inside the droplet. So, meaning that we have a pressure force that acting on this surface and a force that acting around the perimeter. The force acting around the perimeter is the one which is surface tension, and the force that acting inside to balance this surface tension is called pressure forces. So these two need to be balanced. Now we will derive the equation for that one and in here. If we want to derive the force for that one, you can see the surface tension, which is a property in here, times the distance it is acting. What is the distance? Is around this circle, which is 2 pi r. Now, in that case, this is the force due to surface tension. What is the pressure forces? Pressure is acting on this surface, which is surface area of the droplet, which is cut to half, pi square, and okay, which is the surface area of the droplet when it is cut to half, and this pressure acting. Then the pressure can be, in this case, estimated, which is the difference between, basically this is changing pressure, which is the pressure difference between inside the droplet and outside the droplet. And then this pressure difference, when you balance these forces, basically you will have an equation that allowing for you to estimate the surface tension or internal pressure, for example. What is the application of this one? Let's say, for example, you want to create a certain droplet with a nozzle, then you can estimate how the pressure need to be applied, then in between internal and external, and then work on that. Now, if we consider the case for a bubble, or then you can see that bubble, the pressure is same as what we had. If we cut it to half in here, you see the pressure would be the same what we have. Then, however, one thing is different, which is basically the difference is, in this case, the difference in this case is it has two, because the inside the bubble is void, then the surface tension acting around the perimeter inside the bubble, which is inside the bubble, and inside the bubble, which is here, and another one which is outside the bubble. So the difference between bubble and droplet is that there is no surface inside the droplet, however there is another surface inside the bubble. Then the force on the bubble are double. That means that's why you see in this case two. One is outside, one is inside the bubble, basically. So in that case, when we want to estimate the balance the forces due to surface tension and change in pressure, then in that case we just put this one, which is multiplied by 2, and as we explained, and then again pressure difference between inside and outside the bubble, then and the surface area. Once we balance it, this is the equation we're getting. Now you see the difference between droplet and bubble. So the pressure is twice as droplet in case of bubble. One of the other property that or effect that is surface tension could have is called capillary effect. Why capillary effect is important? For example, the plants in arid region normally they feed in terms of water due to this capillary. Imagine you have a layer of soil and somewhere under the soil we have groundwater in here. Then these particles of soil, when they are sitting next to each other, between them they forming like a tube. And then these tubes depend on what the formation of soil is, whether it is sand, gravel, clay, or so on. Then this cause, the capillary effect cause that water move a few meter up and then feed basically the plant which is in here. Now, looking at this figure in here, this is one practice to show surface tension. This has got the lower diameter increase. You can see all these liquid interconnected to these all these six tube, but each tube has different diameter. You can see on the smaller diameter the rise in due to capillary is higher. So what that means, if we want to relate to this one, the smaller the particle of the soil is, the higher the water from groundwater move to near the surface. This is called basically capillary effect, which is due to surface tension. Now, if we put water in a tube or a container, you can see at the or a tube, the water surface looks like this one, like or whatever shows in here. If it is, for example, a smaller one, it is something like this. However, if put mercury, it would be in this way. Yeah, reverse. Now, why is that? Because we said hydrophobic and hydrophilic. Water is hydrophilic, and mercury is hydrophobic. That means why this happened? Because the force or attractive force in mercury molecules are higher, and then this angle normally is larger. That means causing non-wetting surface. That's why, due to this surface tension in here between this wall and mercury in the container, it is standing in this form. So however, for hydrophilic, which is wetting liquid, then it goes up. Remember, for hydrophilic, angle is normally less than 90. However, for hydrophobic, this angle is greater than 90 degree. And that's the difference between wetting and non-wetting fluid, basically. Okay, now that we learned the concept of capillary, we want to come up with the formula and see how we can estimate capillary rise in a tube or between two plates or whatever it is we consider. Now, consider you can see in this case we have put a tube inside the liquid, and you can see that the water level or liquid level is rise to some extent. This is obviously hydrophilic liquid because it is rising, but if we put mercury, it will go lower basically due to what we explained. For example, in this case, mercury will be, if we put a tube in mercury, it will go like that. If we put in water, a liquid like water, it will go up. So let's say we want to work out capillary rise and to see how. Okay, this is force balance basically. The force acting due to surface tension and the force acting due to the force acting due to weight of the water inside this controlled volume. That means you can see the weight of these acting downward should be equal to the normal forces acting upward, which is due to surface tension. And this is basically, if we consider it as a tube, this is the forces acting around perimeter of tube. So in that case, the force due to surface tension would be 2 pi r, which is the perimeter of this tube, times the surface tension coefficient. And this is the force which is due to surface coefficient. Now, why cos phi? Because this is velocity, the force acting in this direction, but we need to balance this with the normal forces. So in that case, now we have surface tension. What is the weight forces? The volume of this one, which would be the surface of that, times distance, which is the volume of that one, times a specific weight, or basically rho g. And then these two forces need to be balanced. Now, if we balance these two forces, then we manipulate all the parameters, and we come up with a formula which is in this yellow box, and this is basically the force which acting the capillary rise can be estimated. Okay, how we do this for mercury? Same way. However, this angle is greater than 90, and then this one would be obviously negative, because this would be negative value and it would be bad. It's same, no difference between the two. So this is how we can estimate the capillary rise. Then if we want to make a tube for, let's say, 5 meter, then we select this 5 meter, then work out the tube, and so on. Okay. Now we almost finished with the property of fluid up to here. Now we move to pressure and fluid statics. Now, objective here is to determine the variation of pressure in a fluid at rest, and calculate pressure using various kind of manometer. How we do calculate the force exerted by fluid at rest on plane or curved submerged surface, analyze the stability of floating and submerged bodies, and analyze the rigid body motion of fluid in container. Obviously, we don't cover all of this at this lecture. We just cover the first two parts in this lecture, this one and this one, and the remainder would be next lecture, and so that we will cover. But this is the next few lecture would be about that. Now, let's we learn about pressure that we already know. Pressure, what is pressure? Pressure is normal force exerted by a fluid per unit area. So pressure is normal force divided by surface area, and what's its unit is Pascal or Newton per square meter. Now you can see, if you want to have a sense of pressure, for example, you can see in here that a person who has got a mass of 70 kilogram and the surface area of his feet is this much, and this person, which is fatter, twice as weight as this person, has got also same surface area. Now you can see, based on this formula, you can see that the pressure in this one is twice as this one, because surface area is same, however the mass of the two people are different, then the pressure applied, if the surface area does not change, it would be same. That's how it is. Now when it comes to the fluid, imagine you have a container and you're making two hole in here. You can see that the hole which is near the water surface is the jet forming here is shorter. However, the lower hole has got higher distance moving. So why this is happening? Because the pressure at here is less than the pressure at here, and we want to learn about these things. What's the unit for the pressure? Obviously we need to know all this unit. We said Pascal is pressure. We have also bar. Sometimes we use bar. 1 bar is 10 to the power of 5 Pascal, or 0.1 megapascal, or 100 kilopascal. And 1 atmosphere is almost 101.325 sorry, 100,000, 1.1000, sorry for that, 1035 Pascal, or 101.325 kilopascal, or 1.01325 bar. And then if we want to describe it by another unit, sometimes they use kilogram force per square meter, which is 9.8 Newton per square centimeter, and so on. We don't need match this unit, but I just want to focus on bar, what means by bar, what means by atmospheric pressure, and what means by Pascal and megapascal, and so on. This is what we need to learn. Don't worry about kilogram forces, but if you notice this in some textbooks, don't surprise, because they use in different units definition. Okay, now we have different type of pressure. We have absolute pressure, gauge pressure, and vacuum pressure. Okay, what is the absolute pressure? Absolute pressure is basically if we have the actual pressure at a given position. It is measured relative to absolute vacuum or absolute zero pressure. That means if this is, for example, absolute pressure in here, then this is any pressure measured with respect to this datum, then pressure is 0, and this is called absolute pressure. That means this datum has a pressure of 0. Any pressure measured with respect to this datum is absolute pressure. For example, when we saying pressure is 1 bar, in that case absolute pressure is 1 bar with respect to 0, meaning here is 0 and here is 1 bar, or 101 kilopascal, and or 1 atmospheric pressure. Now, what is the gauge pressure? If we measure pressure relative to atmospheric pressure, it's a gauge pressure. For example, now where we stand, the atmospheric pressure is 1 bar. So if we measure pressure with respect to this 1 bar, this is called gauge pressure. Anything above 1 bar is a gauge pressure. That means we don't account for atmospheric pressure. Now, if we measure, so for example, looking at this one, we say this is 0 pressure or absolute vacuum in here, then absolute pressure up to where it is 1 atmospheric pressure is here. Then if the gauge pressure is considered relative to atmospheric pressure, so anything above atmospheric pressure is gauge pressure. So the sum of gauge plus atmospheric pressure would be absolute pressure. This is in this case when there is no vacuum. Now, suppose that we have vacuum pressure. Obviously, we said absolute pressure is measured relative to zero pressure or absolute vacuum. In that case, then because we creating vacuum and we consider similar to gauge pressure, we consider vacuum pressure relative to atmospheric pressure. That means any measure which is lower than atmospheric pressure. So atmospheric pressure is this much. Now how much vacuum is this much. Basically the difference between these two would be absolute pressure. However, when we don't have vacuum pressure, you notice that atmospheric pressure is added to gauge pressure to form absolute pressure. But for vacuum case, normally vacuum pressure is deducted from atmospheric pressure, which is giving absolute pressure. And this is very important to notice. We never ever have negative pressure. Some people say negative pressure, but this is a vacuum pressure. Remember, vacuum. And vacuum pressure scientifically should be relative to atmospheric pressure. If we're talking, let's say, zero point 0.5 vacuum, doesn't mean relative to absolute zero pressure. It is relative to atmospheric pressure. Or if we say 0.4, that means 0.4 below atmospheric pressure, not relative to zero. These are the things that you need to notice. Pressure at a point, or it is called Pascal law, meaning that pressure at a point. If we consider one element within a fluid, let's say liquid, so the pressure we can mathematically, and you can refer to your textbooks, we can mathematically show that pressure from all sides is same. That means when these elements goes to its limit goes to 0, that means pressure P1, P2, and P3 are the same. So meaning that if we have a container, within the container, within the container the pressure everywhere within here, the pressure everywhere would be the same, basically here from above, from bottom, because this is a point which is its limit goes to 0. This is called Pascal law. Remember, pressure is not a vector. Pressure is also a scalar, is a quantity. Now, how the pressure is changing, let's say we have a container. We want to know how the pressure is changing with the depth in a liquid. Let's say, for example, if you have a container, and in this container you want to know how the pressure changes as we go further down in the liquid, then in that case you can see that, okay, in that case the pressure at the surface would be, if it is open to atmosphere, the pressure at the surface would be atmospheric pressure, because we know even we are inside this room, the pressure is atmospheric pressure. Now, what will happen if we go down these two liquid below the water surface by how much? By, let's say, h. Then in that case the pressure would be rho gh. That means the pressure from here to there due to this liquid would be rho gh. Okay, now if we want to see what the absolute pressure would be here, then would be atmospheric pressure from here on the surface plus the pressure due to the column of liquid here. This means that, but many cases we don't consider atmospheric pressure, because atmospheric pressure apply from here, from there, and at the end of the day they will cancel each other. But now what we are trying to say, if it is gauge pressure at here would be 0, because it is atmospheric pressure here, but because we consider it as a gauge, and gauge we say it is relative to atmospheric pressure, at here would be 0. What would be at the bottom, depending on how deep it is, then it would be h. That means this vector here is rho gh. That means pressure here. However, as we go further down, pressure linearly changes and increases to its maximum at the bottom of this container in here. So Gauge, if we're talking about absolute pressure, would be this much. If we're talking about gauge pressure, it would be this one. Now you understand. So what the pressure is changing, how the pressure change in liquid, if we consider the point 1, point 2, then the pressure between two different would be in this form, and then from there change in pressure would be in this form. So meaning the slope of this line is minus gamma, if you consider. So this is how the pressure change within liquid linearly at the fluid at rest, it is linearly changes with depth. Normally this type of pressure is considered for liquid, but if it is we have gas inside, because the weight or the pressure due to the column of gas is very minor, rho gh. Even we have h, but this rho is very small, which normally for gases we ignore them and we don't treat them as similar to liquid. Okay, now does the pressure depend on the shape of a container? We say no, as long as its density does not change. Consider this case. Okay, we said pressure change linearly as we go further down. You see in here is P atmosphere, plus as we go down pressure is rho gh, and this is at the bottom, which is maximum pressure. Now the question is that does the pressure along this horizontal is same? Yes, it is same. Why? Because rho gh for all of these along this line is same. How about here? It's still same, because h and rho has not changed. H in this case is here, then the pressure along this one doesn't matter whether here, whether here, whether here, or anywhere is same. Or and again in here, for example, pressure in here and here and here are all same. However, if we have liquid in here, so the pressure in here and here is different. So meaning because we have a column of mercury, that means pressure due to rho mercury GH, and pressure due to the column of water. So this pressure and this pressure, they will add up. However, for here, because the density is same, the pressure at this point and this point are different. But as we said, if the liquid is same, the pressure is, there is no difference between the pressure between the along this horizontal line. Okay. Another Pascal law, it says the pressure applied to a confined fluid increase the pressure through by the same amount. What that means? That means the pressure is transmitted from here. If we apply a pressure here, it will be transmitted here. Let's say if the pressure is 100 Pascal here, at the same point in here the pressure would be 1 Pascal. That means the pressure is transmitted in here, because we're saying liquid are incomparable. This principle is used, and for the jack, how we see we apply minimum force in here and we lifting of few tons very easily. What will happen? You see this surface in here is small. We applying a small pressure to a small surface, but because this pressure is transmitted to here to a larger surface, which is A2, then the force would be area times pressure. So same pressure here, but because the surface area this side is larger, then we can apply more force. And this is the pressure of jack system, how they are working. So in that case, you can see that we can double up, or depend how bigger the surface is, then we apply the more forces, and this is called Pascal law. The other things that we now need to know how to measure what's the pressure unit. We just roughly refer to that. How we measure the pressure, obviously, this is another things. You can see that we have different devices. As you can see here, these devices are used to measure the pressure. How these devices are working is very interesting. You can see, let's say we connect this one to a tube that has got fluid is going, and then we want to measure the pressure at this point in here. Let's we connect this here. What will happen? The liquid or gas go inside, and this is a spring type tube. You see this gray area is like a circle or semicircle, which end of it is basically end of it is free. And what will happen when the pressure is increases? This ring like to open and go this way. Then this pull up another sector in here, and then it is connected to different gear, and this gear is connected to a scale dial in here, and we can measure basically how the pressure normally are measured in these type of devices. Now this is how pressure is measured. This is one way of measuring pressure. Another way is, we use barometer, for example, measure. The person who measured atmospheric pressure and invented barometer was Trosselli, and I think, if I am correct, an Italian scientist who measured the pressure, atmospheric pressure in 17th century. Now, how he did, he had a container which filled with the mercury and a tube which basically filled with mercury, then inverted and put it in the container which was filled with the mercury. Then he leave it here, and because the pressure applied to here, atmospheric pressure applied here, obviously let the flow come down to a certain distance. That means it start to come down, but to a certain distance. Where? That means up to where that this pressure, which is atmospheric pressure, is balanced with the weight of this one, which is rho g h. And in this case, rho is rho hg, mercury. So he noticed that obviously when he inverted this tube in the container filled with the mercury, he noticed that basically the mercury came stand up to h, becomes 760 millimeter of mercury. That means when the liquid in here is up to 760 millimeter, then this shows the atmospheric pressure, because this pressure applied here and this the pressure due to this column of mercury is balanced. And in this way he measured the atmospheric pressure. 1 atmospheric equal to 760 millimeter of mercury, or 760 or 101 kilopascal. These are how he measured with barometer. Okay, manometer is another devices that are used to measure the pressure. For example, if we have, let's say we have a tube which is connected to a pipe, different section of pipe, section 1 and section 2, then because there is a difference between pressure in here when the fluid move and is under pressure, then the pressure here would be, if the fluid goes here, the pressure would be higher in here and lower in here. And if we have another liquid in here, which in this case we put another heavier liquid, then we can see that because the pressure in here is at point 2 is lower, then in that case Because it is lower, then obviously a pressure at point 1 is higher. At point 5, push the fluid inside and it is imbalanced basically. You can see the red color is standing and at edge higher than this point. Then the pressure difference between these 2 points basically would be rho g h due to this column. Or if we have a tank which is filled with gas, then if we connect a manometer to it, then in that case you can see, because there is a pressure here, this pressure applied in here push this liquid down and then push it stand at a point somewhere in here. Then the pressure can be worked out based on atmospheric pressure plus the pressure due to this column. Remember, in the last few slides, we mentioned that pressure, if the liquid is same, pressure at 1 and 2 are the same because the liquid below that one is same. Same for here, at A and B are the same. Why? Because the liquid below that is the same. This is where we can ignore the below line and then just focus on this part. That's again in here you can see pressure at this point and this point are the same. Then the pressure difference would be due to this column. This is how we can work out the pressure. I will explain shortly this one. But if we have a container and we have few different fluid on it, yes, if we want to work out the pressure, obviously the pressure at this point should be added to this column of liquid 1 and then to liquid 2 and then to liquid 3. That's why you see that how this pressure is estimated. P atmospheric, which is due to atmospheric pressure here, due to atmospheric pressure here, then due to this column of fluid, due to column of fluid 2 and column of fluid 2. This is how they add up and we can estimate it. But for this case, I can shortly show you how we can do that or estimate the pressure. Okay, how to estimate? This step is important for a manometer like this. If we want to estimate the pressure difference between the point 2, or if we want, for example, we know pressure at point 1 and we want to estimate pressure at point 2 or the difference, we can simply work out in this one. What we will do, we write or start at one end of manometer. Let's say, for example, start at this point or at this point. Then, let's say we start at this point. We move along this tube, and then as we go down, we add pressure. When we go up, we deduct the pressure. Let's look at this one, for example. At point 1, pressure is P1. Yeah. Now we're moving down. Then pressure due to this column need to be estimated. What is this column? Is density of liquid coming to here times G plus its height. Remember, when we want to pressure always is considered in the distance. We cannot say along the manometer. Remember, this is very important to notice. That means pressure, this moving like this, but we shouldn't add up the column along this one, not this. We should always consider vertical distance. So we move along this line, we said we add. If we move down, we add to it. That means plus rho gh times vertical distance. What is vertical distance? One is A, which is this distance, plus the remainder, which is h. So now we're reaching this point. We said below this point the pressure are same. We ignore that. Why? Because if we add this one and deduct this one, they cancel each other. What's the point to add this? Now we move up. So once we move up, we need to deduct. So pressure due to this need to be deducted. What is the density of this one? Is rho 2. Rho 2 GH. What is this high? Is that one. Then we deduct that one. Still we're going up. We're going up to here, and this is due to this column. So we deduct that one, and again same way. And when we reach to this point, we say this, we moved along this one, and the at the end it should be equal to the pressure at point 2. That's why you see this one. Very simple. So this is the principle. Start from one end, moving along manometer. If we're going down, we add the pressure due to the column of fluid. If we're going up, we deduct. And once we reach to the other end, we equalize the pressure to the other end. This is all these things is explained here in this text. You can read it on your own time and then add it. But simplified form is what I explained. This is one practical example that from your textbooks that you can follow the step that we explained. A manometer is used to measure the pressure of a gas in a tank. The fluid used has a specific gravity of 0.85 and the monitor column is 55 millimeter as is shown in here. Now, as is shown here. Now, if the local atmospheric pressure is 96 kilopascal, determine absolute pressure within the tank. We want to estimate what the pressure within the tank is. Somehow we say pressure in here, what would be the pressure in here, which is P. So we saying we have 1 atmospheric pressure which we add to it, and then we say that okay, we now need to estimate. Assumption in here is that the density gas in the tank is much lower than the density of manometer. So because this is gas in here, we ignore the pressure due to this one. As you remember, I already explained, for gases normally the pressure is very small and we ignore it. Now let's say, for example, now starting from this end, we going down, we add to it because this is gas, we ignore it. Now in this point is same pressure, then we ignore this part, and now we going up. Because we going up, we deduct the pressure basically. Now we minus that one. So I just want to, let me write it this one. Now we saying pressure in here, P. We ignore this one because that one. Now we start from one end here. If we're going up, we deduct. If we're going down, we add. Now we're going up, which is we deduct. Then it would be rho G H. In this case, H is 55 centimeter. Then at the other end, equal to, in here we have P atmospheric because it is open to atmosphere. P atmospheric. Now rearrange this equation and you will see this equation. Simple as that. Now you have different number and then you can put in this equation and then work out what the pressure would be. So pressure in here is 100.6 kilopascal. Simple as that. Now let's look at this another example which you can simply work. The water in a tank is pressurized by air. That means air in here is pressurized. And the pressure is measured by a multi-fluid manometer as shown in this figure. That means this manometer has got multi-fluid. That means one fluid here, another fluid here, mercury, oil, and so on. The tank is located on a mountain at a latitude of 1400 where the atmospheric pressure is 85.6. Determine the air pressure in the tank if H is 0.1, H2 is 0.2 and H3 is 0.35. take the density of water, oil, mercury to be 1000 kilogram, 850, and 13,600 kilogram per cubic meter. Okay, now we say that simply we can start from one end and move to the other end. That doesn't matter. You can start from point 1, move to point 2, or start from point 2, move to point 1. Now, let's say, for example, we start from point 2 and move other way around. Let's say at point 1, we have atmospheric pressure, which is basically atmospheric pressure. Sorry, because we want to go based on this equation, so I don't want to confuse you. We start from point 1. From point 1, you can see that in this case, let me clean this one. Okay, now you can see from 1 is P1. Yeah, okay. P1 is pressure of air in here, which we don't know. Now we moving down, moving up. If we moving down, we add pressure. If we moving up, we deduct the pressure. The first things before you start for a problem like this that become a bit complex, what you can do, you can identify line of equal pressure. For example, for this one, the pressure from here and there same. For this one, the pressure here would be the same. So in that case, we can ignore this one. We can also ignore this one. Yeah. So how it work now? We start from point 1. We going down by how much? By H1. So H1 rho GH. What is the rho here? Rho water in here. Yeah. Now we're reaching to this point. Okay. The pressure in here, if we go up, then we're going down. One is negative, one is positive, cancel each other. That's why I said we ignore that one. Now we are at this point, yeah? Because this is same as this one. Now rho GH1. Then we going down, we add this one. That means the pressure due to this column will be added, which is H2 basically, rho GH2. Now, what the rho should be for oil, because in here we have a column of oil. Then again reaching to this point, pressure at here and there are the same. So we ignore this one. Now we going up, again we deduct the pressure due to mercury, rho GH3. You see the mercury in here, oil in here, and you see from here we going down, we add. This is what we add. We going is same, we going down, we add again. You see, we added due to oil. Now we going up, we deducted due to mercury, then equal to pressure at point 2. What is the pressure at point 2? Is atmospheric pressure, or P2. Then this is how, which one is unknown? Now that we wrote this whole equation, rearrange the equation for the unknown value. What is unknown value is P1. And then this equation now become this equation. So we put the number and then do the calculation. Eventually we found what the pressure at P1 is, which is 130 kilopascal. I hope that you understand now the pressure, how they work. Summary of this lecture 2 is that what we learned: surface tension, capillary effect. We explain how to estimate, how useful is, what the capillary effect is, how to work out. We learn about absolute gauge or vacuum pressure, variation of pressure via elevation, rho GH, which we discussed, and the pressure in a static fluid is constant in the horizontal direction, or Pascal law, that we explained. We also explained barometer, how to measure atmospheric pressure, and then we just jump into manometer, which we explain. And next week we will continue, next lecture we will continue more on to that one. I hope that you have enjoyed this lecture. If there is any question, you can come back to me or give me a call on team, or and then I would be happy to explain and help you to understand the learning material. Thank you for listening. Bye now.